Okay, we're going to talk about heats of reaction in this section. So lots of times we want how much heat would be generated when we do a reaction without actually doing the reaction. It's kind of like we're going to do it in our office or by paper and pencil before we actually try it in real life. So we can do that with values that we already know, find something that we don't know. So it's like a puzzle. So we're going to use something called Hess's law, and it's a way to figure out the heat of a reaction without actually doing it ourselves in the laboratory, so we can try it ourselves. Hess's law. And we're going to allow us to do it, finding the heat of a reaction without actually physically doing it. We're going to do it indirectly. So we're going to use this kind of like a little puzzle situation. If you like puzzles, Hess's law is for you. And we're going to use different thermochemical equations, move them back and forth, turn them around, flip them, multiply them, divide them to get to where we want to be in our final equation. So it's like a logic puzzle. So for example, if we had carbon, which is graphite like in your pencil, and we had oxygen, it has a lot of energy. And we reacted it, it would release energy exothermically to give us carbon dioxide. So when we burn carbon, we are releasing energy, which is like when you burn gasoline in your car, you're releasing energy, you're doing work and you're releasing energy, exothermic. So, but what if we don't want to really do it? What if we know this whole entire reaction, we know this whole one here, but what if we don't know this other one here? Can we use all this information that we know so far to figure out that unknown? Yeah, so if we know this whole reaction, and we know this partial reaction, and this other reaction that makes CO2 and it changes carbon monoxide into oxygen, we can use these two sets of information to figure out this unknown part. So we can take this number and figure out this difference right here, and that's going to be what we're going to do when we use Hess's law. And then we can just subtract and we figure out that the difference is 110.5 is the difference between those two. So that's how we'll use Hess's law for something that we don't know. We don't know how this could go to there. What is that energy difference? So we use the things that we know. We knew this one and we knew that one to get this unknown one. So we can take diamond, we can add oxygen to it, it turns into CO2. And we know this one, graphite and oxygen makes CO2, but we don't know what would happen if we actually went from carbon diamond to carbon graphite by just subtracting those two, and we could figure out there's a difference of 1.9. Okay? So to do this, we have to use something called standard heats of formation, and it's how much energy it takes to make a particular molecule. And so when we use this standard heat of formation, it looks like this. We'll get these from charts. There's tons and tons of charts, and you can look online to find all the heats of formation of different things. We'll take the products minus the reactants, and we'll get the overall change, just like we just showed in those last two slides. Okay, so you're going to find tables and tables and tables of delta HFs that you can use to figure out something new that you'd like to look at. So here's the standard heat of formation of water. It's saying that it takes hydrogen and oxygen to make 1 mole of water. So that's what this number right here is from this chart. Let's see if it's on this chart. Gas to liquid. Gas to liquid. Well, we're going to use that information here. We want to know how we could form liquid water. And so we look at this chart back here to look for liquid water. So that's what this is saying. To make liquid water, we need hydrogen and we need oxygen to make liquid water, and it generates this amount of exothermic energy when we do that. We need hydrogen and we need oxygen to make water. And we have to have just 1 mole of this, so that's why you have to have a half of this and 1 of those to make this work. So when we're talking about standard heats of formation, it's per 1 mole. So I have to end up with 1 mole right there. So what if we wanted to find out how to make carbon dioxide? So we would need to know about oxygen, carbon monoxide, and carbon dioxide to do this reaction. And we would have to balance this equation of CO plus O2 forming CO2. And we want to find out just 1 mole of this. So we need to make sure that we balance the equation. And when we do thermochemical reactions, we can have fractional amounts of things. When we normally balance things, we have to have whole numbers, but when we do thermochemical, we can do fractions of moles because we want to have 1 mole of our answer. So this is a little different. So this is something new you'll have to get used to. So first we're going to write the equation. We want to have, this is the balanced equation here, but when we look at the numbers on the chart, it's for 1 mole. So we have to make sure we remember that when we go back and look at things. So if you notice, this is for 1 mole, 1 mole, 1 mole. And we're going to have to use that information to figure out 2 moles because this is the balanced equation. So you could either can divide all this by 2 and then use this value from the chart for 1 mole, or you can have a balanced equation like we normally balance equations and then remember you have 2 moles. So you have to remember the number off the chart is for 1 mole of your product. So remember that. That's something it's easy to make a mistake on. So we're going to talk about this balanced equation when we have 2 moles. So that's going to make that many joules when we have 2 moles of this. And then we're going to find the delta H of the product. And we want to have, we're going to make 2 moles of this, so we're going to use that delta H for this guy, and it's going to be times 2, so for that. So these numbers are from the chart, and they're per 1 mole, so that's the definition. So if you have a different amount from your balanced equation, you have to remember that. So we're going to have the products minus the reactants. So the products are CO2. We're going to use the CO2 number here, minus the reactants. Anything all by itself, diatomics are 0, so that's what we got when we looked at the chart. But we did have a number for this, and we figured it out to be negative 221. So this minus that, it's going to give us this answer. So products, delta H of products minus delta H of reactants is the way we do these things. And here's some for you to try. And let's look at forming something. Standard heats of formation. Here's another one. We have a delta H of negative 787 kilojoules for this reaction, but we're talking about definition of delta HF is per mole, so we'd have to divide that in half to get that. And what if we were, so that's, if we go all the way, it's going to make that much heat. If we go halfway, we're going to make this much heat. So it just depends on the reaction we're talking about, how much heat you're going to make. So let's see how you do on this one. According to Hess's law, it is possible to calculate an unknown heat of reaction by using what? So we're going to use 2 reactions when we know the heats of those reactions. 2 or more, actually. Okay, heat of formation for chlorine gas at 25 is the same, or is, sorry, I don't want to, so figure out what you think the answer is. So this is chlorine gas, so this is kind of a confusing one because, so anything diatomic is always 0. So you're going to see that on charts. When you see things that are diatomic, they're going to have a heat of formation of 0. So this one you're going to have to pause me and try this one so that you can figure this one out. So remember products minus reactants. Luckily, these are all 1 mole things, so it should be pretty easy. So you should get that one if you do it correctly. So we're done with that. Thermochemistry is not super straightforward, so you have to really try these a lot until you get good with the math and understand what's going on. And we'll have more on Hess's law as well. All right, in the book. I'll talk to you soon. Okay, bye-bye.